Section 9.7, differentiation of exponential and logarithmic functions. So we should first of all recall what the graph of e to the x looks like, and there it is in green. It is the natural exponential function we're going to be working with, and also its inversely related function, the natural logarithm function of x, which is the one here in red. So, first thing, the derivative of the exponential function. Specifically, in this class, we're just going to look at e to the x. So you don't have to worry about any other exponential type functions other than this natural one. So notice that the derivative with respect to x of e to the x is just e to the x. So that's nice. So let's see how this works by way of some examples. So find the derivative of each of the following functions. Number one. Well, notice here the function f is equal to 4x cubed times e to the x. So what we're going to have to use here is something we have already studied, and that is the product rule. So the derivative of this function, f, which is f prime of x, is going to be equal to what? The second times the derivative of the first. By the way, this is my first. This e to the x is my second. So e to the x times the derivative of the first, which is 12x squared, plus the first, 4x cubed, times the derivative of the second, which, remember, the derivative of e to the x is just e to the x. And you can just leave it just like this. Now, with that being said, down the road, we will have to be able to simplify these things so we can use them to answer some more, questions. So notice that the GCF here of both of these expressions is what? The GCF is actually 4x squared, there's your x squared, e to the x. So what I'm doing now is not calculus. This is just a review of factoring out the GCF, which is going to allow me to rewrite this so that down the road, it's going to be easier to set this equal to 0 and solve for x. Okay, let's go on to the next example. Ooh, a quotient, which means we have to use the quotient rule. Can't simplify this, so let's go ahead and review another rule from the past, our quotient rule. So what does that tell us? It tells us it's the low. There's our low. D high is just e to the x again, minus high, which is e to the x, times d low. Now d low is what? The derivative of e to the x is e to the x, and the derivative of a constant is always 0. So the derivative of this low, this denominator, is simply e to the x. Then we finish it out by doing what? Low, low. And here again, we really should understand that this could be simplified into what? You get e to the x times e to the x. That's going to be e to the 2x minus another e to the 2x, okay? E to the x times e to the x is the same as e to the 2x. All right, so in other words, we have e to the 2x minus e to the 2x. Those are gone. We're just left with this on top and the same denominator, e to the x plus 8 squared. Okay, you're not going to have to simplify it like this in WebAssign, okay? You can leave it just like this. But I'm just telling you, down the road, once we get to chapter 10, you're going to want to be able to simplify it so that you can apply it. All right. Example number 3. Ooh, this looks like a chain rule situation. So let's review that rule from the past, the chain rule. So the derivative of the outside would be 10, leaving the inside the same, to the 9th. The derivative of the outside, 10, times keeping the inside the same to the 9th, times the derivative of the interior, which is just going to be e to the x. Okay, the derivative of e to the x is always just e to the x. Derivative of a constant is just 0, so that's why it's just e to the x. Okay, so this one really not much you can do with it. If you wanted to, you could write it like this. Put the 10 and the e to the x together, and then rewrite everything else. Again, at this point, either one would be acceptable in WebAssign, but down the road, you're going to want to make sure you know how to simplify these expressions. Okay, the next thing we want to look at is the chain rule specifically now for exponential functions. So what if we have a function that's e to the something in terms of x, not just e to the x, but something like e to the 5x plus 7 or something like that? Well, in order to take the derivative of this with respect to x, we're going to leave whatever it is, whatever has been given to us exactly the same, and then multiply the original by the derivative of the exponent. So let's see how this works by looking at some examples. All right, so the derivative of this function, f prime of x, is going to be based on the chain rule for exponential functions. So what does that mean again? Well, first of all, the constant multiple rule applies here. That 7 remains, okay? So it's going to be 7 times e to the 3x plus 2. This part stays exactly the same. And then what you're going to do is you're going to multiply this by the derivative of the exponent. So this part stays exactly the same. And the chain rule means we now multiply this same piece by the derivative of this exponent, which is just 3. So f prime of x is going to be equal to 21 e to the 3x plus 2. All right. Let's look at this one. So this one, a little bit more complicated, I guess. I guess it really depends on how you see it. I'll try to keep this as straightforward as possible. So we do have to use the chain rule for, the overall function. But within that, we also have to know how to differentiate e to the negative 2x. So let's see how this works. F prime of x would be equal to the derivative of the exterior, keeping the interior the same. So there's our first part. Now times the derivative of the interior. So I'll just use parentheses to indicate the operation of multiplication. So what's the derivative of the interior? Well, the derivative of 1 is 0. And what's the derivative of e to the negative 2x? Well, that's based on the chain rule for exponential functions. So it's e to the negative 2x times the derivative of this exponent times then what? What's the derivative of negative 2x? It's negative 2. So there you go. Now, if you really wanted to, you could rewrite this. So let's see what we're going to get here. Well, I'm going to put a division bar. You're going to see why in a minute. What's 4 times negative 2? It's negative 8. This part stays the same. 1 plus e to the negative 2x cubed. This part, remember, it's just 4 times this, times this, times this. So this part we haven't messed with yet. It's e to the negative 2x. And we remember we'll be with the negative exponent. That means we can invert the base. In this case, it goes from the numerator to the denominator. And this is what it would look like. All right. Example number 6. Find the second derivative of this function. Well, in order to do that, we have to first come up with the first derivative, f prime of x. So, how are we going to do that? Well, let's see. This first term would be 8 e to the negative 3x times the derivative of this exponent, which is negative 3. That's the derivative of this first term. And then minus 5e to the negative x times what? The derivative again of this exponent. And the derivative of negative x is just negative 1. And so the first derivative would be equal to what? Negative 24 e to the negative 3x plus, because a negative times a negative is a positive, plus 5e to the negative x. That's our first derivative. Okay, what's our second derivative? Well, the second derivative is just the derivative of the first. So here we go again. Negative 24 e to the negative 3x times the derivative of this exponent, which is negative 3, plus 5e to the negative x times, again, the derivative of this exponent, which is still negative 1. And so, finally, we would get what? Negative 24 times negative 3 would be a positive 72. E to the negative 3x. And then positive 5 times negative 1 is negative 5 e to the negative x. Interestingly, the second derivative here is equal to the original expression of our given function f. Anywho, this is the second derivative of the function f.